to Theory of Flight. I'm your host, Ray Preston, and we're continuing our discussion of how the aerodynamic force is created. Now, you'll remember that last time I asked you to meet me out in the parking lot so that we could talk about wind. And it's a perfect day for it, beautiful day. There's just a very light breeze, about 5 knots, blowing from over in that direction, which happens to be north. And so the question I have for you is, when there's a 5-knot wind, what image do you have of the air particles? What are the air particles doing? Do you imagine all the air particles drifting past me at 5 knots, just like that? Now, if you do, that's exactly what Isaac Newton would have thought, so it's certainly not a foolish thing to think. But if you remember, last time we learned that modern scientists believe in something known as the kinetic theory of gas. And the kinetic theory of gas says that the air particles are actually moving at hundreds and hundreds of knots. And the only thing that determines the velocity that they move at is the air temperature. Now, that being the case, there cannot be particles of air drifting past me at 5 knots. If there's an oxygen molecule anywhere on this planet moving at 5 knots, it's part of a solid hunk of frozen oxygen. There's no way that atmospheric particles can move that slowly. So how am I to make sense of a 5-knot breeze if the air particles themselves are moving at hundreds of knots? Now, the first secret here is to avoid any temptation to start theorizing. We don't need to come up with a new theory to explain this. This is the beauty of science. What we have is a theory already called the kinetic theory of gas. And the kinetic theory of gas needs to predict wind for us. If it doesn't, we're going to have to invalidate the kinetic theory of gas to get a new theory. But actually, if you think about it just a little bit, the kinetic theory of gas does predict wind. In fact, it predicts wind in 2 specific ways. Let's go over each of them in turn. So, option number 1 for wind would be to say, let's just imagine that the sun is shining brightly over there. It's a nice, beautiful, warm day, and the ground is absorbing the sun's energy. And all the air molecules over there have been warmed up to the point where they're moving at 650 knots. Let's say over here to the south, it's just a few degrees cooler. It could be that there's a couple of clouds shading the sun, or it could be that the ground is a slightly lighter color. And notice here that I'm using other theoretical concepts to explain why the temperature would be different. But the point is that for whatever reason, it's just a few degrees cooler over here, and as a consequence, the air molecules are only moving at 645 knots, if you're allowed to say only 645 knots. So I stand in the middle, and I'm being bombarded. All the air molecules coming at me from over here are hitting me at 650 knots. And all the air molecules coming from over here, they're hitting me at 645 knots. Now, the other variable that I need to take into account is the quantity. So imagine that I grab a handful of air over here and I count the molecules. I go 1, 2, 3, 100 trillion. And I grab the same volume of air molecules from over here, and it's also 100 trillion. That means that since the molecules are moving randomly, the same number of molecules should hit me from this side that hit me from that side. The only difference is the ones from over here, they bounce off me at 650 knots, and the ones on this side bounce off me at 645 knots, a 5-knot difference. Now, will I be able to tell that difference? The answer is yes. I feel slightly more force pushing me this way. It's not a lot, but just a little bit of force. And my life's experience has taught me to call that small force that I feel a 5-knot wind. Now, I said there were two mechanisms, and really the second mechanism is almost being implied there. Imagine in the second case that the temperature is the same everywhere. So the air molecules over there, they're moving 650 knots. And the air molecules over there, they're also moving at 650 knots because remember, temperature determines the velocity of the air molecules. So every time a molecule bounces off me this side, it bounces off at 650 knots. Same thing over here, so the forces are equal on a molecule per molecule basis. But what if by some mechanism, and we'll discuss in the next episode what that mechanism would be, but by some mechanism, a few of the molecules over here are being taken away. So now, in a handful of air, over here there's still 100 trillion air molecules. But if I grab a handful over here, now there's only 99 trillion air molecules, 1% fewer. So now for every 100 molecules that bounces off me on this side, only 99 would bounce off me on that side. Now would I be able to tell that 1% difference? The answer once again is yes, I can. In fact, if you think about it, 650 knots, 1% of 650 is 6.5 knots. If that 1% difference was the case, I would be saying it's a 6.5 knot breeze today. So if in fact it's a 5 knot breeze, that would mean the density would need to be just a bit less than a 1% difference on my two sides. Now at this point, scientists get all excited. They realize that not only has the kinetic theory of gas predicted wind, but it's given a mechanism. In fact, it's given two mechanisms for wind. And that opens up the opportunity for more experiments to test the kinetic theory and see if it can be confirmed. Remember, we can't strictly speaking confirm, but we have opportunities now to run experiments that have the potential to be inconsistent. And so scientists investigate, and I'm sure you learned in meteorology class that they've come to the conclusion that wind is indeed caused by temperature differences from place to place on the Earth. But scientists also realize there's a problem here, because if you think about it, we've got the temperature difference making wind, and we've got a density difference making wind. These two things, they could work together or they could work against each other. For example, on one day it might be just very slightly warmer over there, but it's also just slightly more dense. Over here, a couple of degrees cooler and just fractionally less dense. Now that could also explain the 5 knot wind. But it's equally possible that there could be a day when it's a few degrees warmer over here, so the air molecules are moving faster, say 650 knots over there. Over here it's a few degrees cooler, so the air molecules are only moving at 645 knots, but maybe it's slightly more dense, just a bit less than 1% more dense over there. So now the molecules bounce off me on this side at 650 knots and they make a certain force. The molecules bounce off me on this side at 645, they make a bit less force, but if there's more of them, maybe 1% more, then the effect would cancel itself out and there would be no wind. And remember, all the wind is the force. Right? We can't really see wind. When we say that we experience wind, all we're really saying is we're experiencing that force pushing us. And we attribute that to what we've learned to call wind. So science says, well, we can't let this go like that. There's got to be some way of explaining the unification of the density and the temperature effect. We're going to have to come up with a formula that will allow people to predict the wind, the airflow, based on a combination of temperature and density. We're going to need a name for this concept. We're going to come up with a really cool name. What shall we call it? I know. Let's call it pressure. And so, of course, that's exactly what scientists do. They come up with an equation. They call it the gas law equation. And the gas law equation simply says that pressure is equal to R, where R is just a unit correction factor called the gas law constant. multiplied times the density multiplied times the temperature. So the gas law, simply pressure is equal to the gas law constant multiplied times the temperature multiplied times the density. It's as simple as that. Now, of course, up until just this moment, you were thinking that pressure is kind of a fundamental concept that can't be broken down, but now you realize that pressure is in fact a compound concept. It is the compound of temperature and density. So when you look at your meteorology charts and you see on a particular day that it's 1,000 millibars over there, that's one of the common pressure units that we use in aviation, and it's 900 millibars over there. That's a 10% difference in the pressure. You're thinking 10% of 650 knots, that's like 65 knots. We would expect a 65 knot gale blowing past us, and that's in fact exactly what would happen. Now there's a little bit more to it than that. We'd have to take into account the friction, but essentially that's it. So, as you probably already knew, air flows because of pressure difference, but now we have a deeper understanding of what we mean by pressure. It's really just the combination of temperature and density. So, in meteorology, it turns out that the vast majority of wind is the result of temperature differences from one place to the other on the Earth. And as you'll see as we complete this series, the airflow around a wing is mostly the result of density differences. But in either case, they can be referred to as pressure differences. And there you have it. So hopefully you can see where we're going with that. Next time, I'd like to meet you back in the classroom. And try not to drop the ball on this one. Well, actually, I am going to drop a ball next time, and we're going to discuss how the aerodynamic force forms above a falling ball. Okay, so until next time, we're out of time for today, but until next time, I'm Ray Preston, and this is Theory of Flight.